The Rutherford gold foil experiment, conducted by Ernest Rutherford in 1909, was a groundbreaking experiment that led to the discovery of the atomic nucleus. Before this experiment, the prevailing atomic model was J.J. Thomson's plum pudding model, which suggested that atoms were composed of a positively charged substance with negatively charged electrons embedded within, like raisins in a pudding. However, Rutherford's experiment provided evidence that atoms have a dense, positively charged nucleus at their center, surrounded by mostly empty space. This simulation aims to help students visualize and understand the gold foil experiment, how Rutherford interpreted the results, and how this led to the development of the nuclear atomic model. By engaging in this interactive thought experiment, students will grasp the concept of atomic structure and the significance of Rutherford's findings. To simulate Rutherford's gold foil experiment in a classroom setting, students can imagine themselves as scientists observing the behavior of particles as they interact with matter. The experiment involved shooting tiny, fast-moving alpha particles, positively charged helium nuclei, at an extremely thin sheet of gold foil and observing their deflections. To begin the simulation, students will need to imagine the following setup. A source of alpha particles. This can be visualized as a device emitting tiny, positively charged particles at high speeds. In reality, Rutherford used a radioactive element like radium to produce these alpha particles. A thin gold foil. The gold foil is extremely thin, just a few atoms thick, allowing the alpha particles to pass through or deflect. A circular fluorescent screen. Surrounding the foil is a screen coated with zinc sulfide, which lights up whenever an alpha particle strikes it. This helps in tracking the paths of the particles. Students should imagine standing in a dark room, with a tiny glowing dot appearing on the screen each time an alpha particle makes contact. By carefully analyzing where the dots appear, they can deduce how the particles interact with the gold atoms. Now that the experiment setup is in place, let's visualize what happens when the alpha particles are fired at the gold foil. Students will observe that the majority of alpha particles travel directly through the gold foil without being deflected. This suggests that atoms are mostly empty space. A small number of alpha particles deviate slightly from their path. This implies that they are encountering something within the atom that exerts a weak force on them. Surprisingly, some alpha particles rebound almost straight back. This indicates that they have collided with a very dense and positively charged object within the atom. At this stage, students should start questioning what could cause such an unexpected deflection. If the plum pudding model were correct, all particles should have passed through with minimal deflection. Rutherford and his team carefully analyzed the data and reached the following conclusions. That since most of the alpha particles passed straight through without being deflected, Rutherford reasoned that atoms must be largely empty space. This overturned the previous assumption that positive and negative charges were spread evenly throughout the atom. The rare but significant instances of large deflections suggested that the positive charge in an atom is concentrated in a tiny, dense center called the nucleus. This nucleus contains most of the atom's mass. Since the nucleus is positively charged, the negatively charged electrons must be moving around it in some way to balance the charge. This idea laid the foundation for later atomic models, including Bohr's model. Through this simulation, students should visualize that instead of a uniform spread of charges, atoms have a tiny, massive core, the nucleus, surrounded by electrons moving through mostly empty space. To further deepen understanding, students can perform additional thought experiments and analyze different conditions. Students can imagine repeating the experiment with a thinner or thicker sheet of metal, such as silver or copper. How would the results change? The principles remain the same, but denser metals would cause more frequent deflections. If the experiment used neutral particles like neutrons, the results would be different because neutrons would not be repelled by the positive nucleus. This highlights the role of electrostatic forces. If the alpha particles were fired at lower speeds, they might be deflected more easily, showing how kinetic energy affects atomic interactions. Encouraging students to imagine and predict different outcomes will help them engage more deeply with the concepts of atomic structure and experimental physics. Understanding atomic structure has led to significant scientific and technological advancements. Some key applications include: knowledge of atomic nuclei has contributed to the development of nuclear power, medical imaging, like PET scans, and radiation therapy for cancer treatment. Rutherford's findings paved the way for quantum theory, which describes how electrons behave around the nucleus. By understanding atomic interactions, scientists can design stronger materials and develop microscopic technologies for various industries. Students should recognize that what began as a simple experiment over a century ago has shaped much of modern science and technology. Through this simulation of Rutherford's gold foil experiment, students gain insight into how scientific discovery progresses through observation, experimentation, and critical thinking. The surprising results of the experiment led to a fundamental shift in our understanding of atomic structure, disproving earlier models and introducing the nuclear model of the atom. By visualizing the movement of alpha particles and their interactions with gold atoms, students can grasp key concepts about the atom's nucleus, the role of empty space, and the forces at play inside an atom. This knowledge not only helps in understanding physics, but also provides a foundation for fields like chemistry, engineering, and material science. By immersing themselves in this simulated thought experiment, students develop a deeper appreciation for scientific inquiry and the power of experimentation in uncovering the hidden structure of the universe.